all these concepts, they are formed because, well, they take a certain amount of studying to understand the physics behind it. So before we came along with our equipment back in the early 90s, people had to do this by hand, and you had to have a geophysicist to actually do the work, because it's a lot of math. You have to understand what you're actually doing. You have to understand the filtering, all these things I mentioned. So what we did was, the very first innovation, which we thought was really innovative in the late 80s, was just to put a microcontroller in there. But you remember that in today's world, that's not a big deal, because we're used to smartphones and high-def cameras. But I mean, before Windows 95, we had DOS, or Windows 3.1.
Mm-hmm.
The world was not very high-tech, really, in terms of today, right? So the next thing we did was we put electronics out at the electrodes that would automatically turn one of these stakes into either AB or MN, so that we could make all these different measurements. And then we had the multiple channels so that you could do it very quickly. And we tried to abstract the technology away from the user, so you didn't have to really know what you're doing other than just set up an equal spacing. And then we designed software that takes this data and then calculates the resistivity response of the Earth for you, so you end up with a nice, beautiful picture where you can see some structure in the Earth associated with the different types of rock types and materials and minerals and things like that. Let's talk about the depth of penetration and resolution. So you know that resolution is half of the electrospacing. So if the electrospacing is 10 meters, you wouldn't be able to see anything better than 5 meters, right? If it's 1 centimeter spacing, then you wouldn't be able to see anything better than half a centimeter. But of course, on your scale, because you want to get depth, you know that the distance you spread these out increases depth, but then lowers the resolution. So a rule of thumb here is that you can see about 20% of the length, right? That you spread out. Okay, so if you take 100 meters of cable, and you place a certain amount of electrodes there, it doesn't matter the number of electrodes, because we're talking about depth right now. You will get 20% of 100 meters, 20 meters, right? That makes sense, right?
Right.
So if you want to get down deeper, like 30 meters, we can just take 30 meters, and we can divide it by 0.2. And let's see here, that gives you, I think, 167, right? If I remember right. Let's see. So we just do 30 divided by 0.2, 150, sorry. Okay. So then we look at, the next step we would look at is, what's the resolution you need, right? Well, if you think of the resolution, it depends on the spacing, right? But to increase the signal quality, we can open this receiver dipole up or make it smaller. You know, if we spread A and B out further, the voltage becomes smaller, so we have to open it up to measure a larger voltage. But then we lose resolution, because we just, instead of 1 electrode spacing, it's not like 3 electrodes, right?
Mm-hmm.
So now the electrode spacing is no longer, you know, let's say 1 meter, it's 3 meters. So if you divide 3 by 2, your resolution is 1.5 meters, right?
Right. Want to interrupt you here, just to get it through. If we're going 30 meters in depth, we're only going to see 20%, or the resolution would be 20% of 30 meters, right?
No, the resolution has to do with the electrode spacing. So if I decide that I have to spread out my sensors at least 150, sorry, let's put this here, 150 meters on the surface to reach 30 meters, how many electrodes do I want to put within that 150 meters? Now our systems are 28 electrode, 56, 84, and 112. You could potentially go up beyond that, but you're talking about the cost of the systems becoming more and more expensive. And then I have to advise you, at some point, you're really just affecting the resolution near surface rather than at depth. Every geophysical technique has limitations. Ours is the resolution with depth, right? Radar doesn't have that. Their limitation is like conductive stuff. They can't see through it very well, right?
Okay.
So
if we're going to be looking at 30 meters in depth, the 20% rule is that for A and B to be 150 meters, or the cable would be have to 150 meters, right?
Yes.
Okay.
Well, the cable can be much longer, but as long as you know, for whatever survey you're designing, you need 150 meters. So if you had 300 meters of cable, you would just, bring the cable in.
Right.
You have a little bit of slack between each one.
Okay. So, and that's 150 meters between the A and B transmitters, right?
Mm-hmm.
And then the receivers, depending on how wide apart those are, where that is, that would give you the resolution.
Yes. Right.
Okay.
So you have to apply more electrodes, more of these positions in order to get better resolution with depth.
But then, if you putting them too close, all you're getting is the surface rather than the depth.
Well, you're always going to get the depth also, but the thing is that the resolution is mostly improved in the near surface. So the way that we could divide this 30 meters, so 20% up, and let's say about 3 intervals, okay? And really, what I try to tell clients that because there's noise and things like that, I try to be more realistic here with 15%. You may get more or less, but the thing is, the 15% I know from experience, anywhere in the world you always get.
Okay.
The 20%, because you're separating the transmitter receiver, you get more susceptible to noise. In some areas it's easy to do 20%, some it's more difficult.
So
A lot of this has to do, the depth of penetration and the quality of the data has a lot to do with how well you prep the connection here to the ground.
Meaning how?
Because what's important for us, our transmitter, our signal is the current. So we have to get enough current in there. And because if the ground is very dry, in your case it's sand, dry sand, that's probably a more difficult case.
Pouring water on the transmitter or in
Stake,
that area.
right. Usually we pour like a pint of water or a liter or so at the stake to kind of increase the surface area of that stake.
Okay.
Yeah.
And that will increase.
That will increase the amount of current you can put in the ground.
Okay.
Yeah. So, in any case, let's say if we were to divide this into 3 intervals, maybe approximately like 6% here, 12% here, and we'll say 18% here. Given that this is kind of arbitrary, just a rule of thumb. Okay.
Mm-hmm.
So you can imagine that this measurements down to this point have, half of. Let's say if the unit spacing is 1 meter here.
Mm-hmm.
Well, then you're going to have about 0.5 meter resolution here, right? But to get down to here, you have to increase instead of just doing that, you may have to increase to, 2 meters to get down deeper because your signal disappears as A and B gets larger, right? So it's a continuous kind of give and take here. We want to go deeper and deeper and deeper, but not so, to the point where we still have a signal, and then at that point, if the signal is too low, we increase the dipole and sacrifice a little bit of resolution to get deeper. So here you can imagine what's the half of 2 meters, so that's 1 meter, right? And of course, if we go down even further, 3 meter spacing, here, like our readings or the transmitter, you basically come down to, 3 divided by 2, yeah, 1.5. So do you see that there's a relationship with the resolution actually decreases as you go down?
So, in relation to the resolution, we're talking about that the object would have to be 1.5 meters for us to be able to see it.
Right. So the thing is with amber, and this is something you're going to have to work out and find out. I can erase this. I think the camera does this. Okay. So, you have to forgive me because I'm not an expert of finding amber.
Right.
So I have to draw some correlation to things that I do know. And that is that one thing is that the material contributes to the overall resistivity there. So in my mind, and I think this is correct, but you're going to have to double check this, but I think the amber, one thing is that just by the idea you tell me that it floats to the surface, and just holding my wife's jewelry, amber is incredibly light. Like, it's not dense, right? So, yeah, I mean, this is incredibly light, right?
Right.
So that's like it's mostly air. Now, so if you have, you want to find a deposit of this stuff, right?
Right.
So I imagine that after speaking with some of my colleagues here, we're discussing this. The amber forms from insects burrowing into a tree and or is damaged and the sap pours out and
Right.
and comes like a lump right there. So if you find one tree like this, there's probably an infestation of insects that done this to probably the entire forest there, and then you have these nice areas of deposits. Otherwise, they would just be very random,
Right.
right? You wouldn't find them everywhere. So, and that's some of our. I'm sorry, I'm just thinking here. It's some of our assumptions. We have to think, what's realistic. So, the idea is that if you have these kind of deposits, you want to find quality areas to explore. There's going to be areas where it's maybe used for like medicinal, where it's not large chunks you can make jewelry out of, and there's going to be ones that are like large chunks, right? But if you have enough of this stuff in a given volume of material, this will contribute to a very high resistance because it has no porosity. There's no pore space in there.
And that's exactly the case. Typically, when it's found, so the way that it's mined now is that they'll take like a fire hose, except extremely flexible and light, hook it up to a power pump with water, and they'll actually, because it's sand and kind of like turf, they'll just push it right into the ground, and it'll go as deep as 30 meters in the ground, and then it just flows to the surface, and you can gather it there.
Right.
And typically, the way it's found is, so if they hit a spot, they'll just keep the hose there, and it just keeps coming up.
Yeah.
So we're assuming that they're typically in large clusters, and
Yeah.
you could pull 2-3 kilos out of one area sometimes.
And you don't even know if you're getting it all.
Right.
You're only getting stuff that's dislodged that can actually float up.
Exactly.
So the idea is, I think that once you've pumped the area, forget about doing imaging because you've disturbed it so much that it's just you're gonna see the path that you drilled and infiltration that water had moved things apart.
Right, and that's the idea, is that we're looking at almost seven sites right now that haven't been disturbed, and rather than going in there and start excavating or pumping water into it, we can actually see where it is and maybe even eliminate 90% of the work.
Yeah. So a lot of times with mining, and this is a correlation with, or corollary with placer gold, and that's of course gold is different from amber in that it's very dense. So it wants to go down until it finds like bedrock or some layer that is impermeable to it. So in that case, they're always fighting the cost of diesel and manpower, because if you could just excavate all the ground without any cost, then it wouldn't matter, right? You would just excavate everything. But what they really want to do is they want to find only deposits of sand and gravel, because that's where the gold has been able to settle down. Clays and silts are so fine grained that there's no potential for it to move over geologic time, right, to the bottom. So they really just want to pinpoint those areas so that they spend their diesel and manpower excavating those areas that are actually worthwhile, because you're getting an ounce per however many cubic meters or yards of material you pull out. So that's the cost of diesel to move that out in time. So you're always fighting that, right? The expense of actually the exploration with, or the mining with what you can, the revenue you make from the product you're getting out, right? I think it's similar to what you guys are doing. In your case, though, I would imagine that this stuff is getting trapped at impermeable areas where it stops it from going up. Because over geologic time, less dense things will actually start floating to the surface. We know this very well from in the oil field. Some of the reservoirs, and I would say many of them, were found with salt domes. Salt domes is less dense, and it starts as a layer of deposited on, like, for example, like a sea floor or a lake floor, and kind of an area where you have a lot of evaporation. So you get a lot of salt content there. And what happens is over time that this stuff starts moving up like this, like a bubble, and kind of breaking up the layers of sedimentary rock like limestone and sandstones. And what happens is that the oil migrates along these things, which have been pushed up by the salt. It's just a matter of physics. Over time, everything will move. And I think the amber probably, in the process of millions of years, probably has a tendency to move upwards too, but it can only move until it gets stopped.
And what would stop it again?
Well, anything that would be impermeable to it, anything that is too rigid, for example, right? So what you have over geologic time is that you have these. You gotta imagine like the rock layer. Basically is a record of all the physical processes that led to the deposition of the sediments there, to burial. You know, a lot of the rock is only going to lithify if it has enough pressure on it. So the rock that we see now at our surface was usually buried, you know, several kilometers deep. For example, the limestone you see here was deposited down towards the equator. We're now in Texas, which is nowhere near the equator. But the plates have moved since that time, and we can track that movement. So we know, you know, we know the ages of these rocks. We know that they can only be deposited and lithified under great pressure. So we know that, you know, a kilometer or several kilometers of rock formed above it to give enough pressure on those rocks to become limestones. And of course, limestone comes from, you know, remains of animals. You know, the calcium carbonate out of shells from sea life. So I think that there's probably some similar type of process with amber. The thing that what you're telling me is that it's less dense. So that's a very good thing, because you know that it's mobile within the, especially if it's in a loose sand, right? So I think that the way you would detect it is that, you know, of course you would have to test this in the field, is that you would look for areas that inhibit that flow or that movement of that amber over time.
Mm-hmm.
You may find that you'll find deposits where it kind of gathers, you know, or, you know, things like this. If you have some kind of horizon of clay, for example. Clay is weathered rock, so it's just rock that's been weathered into very fine particles like minerals and then deposited in very low energy water environment, okay, typically. So if you have amber down here and there's some mobility, you know, the time it took to deposit this could be, you know, millions of years, or it could be, you know, a very quick event that, you know, let's say flooding and then deposit a bunch of sand down, or maybe with sand dunes blown in and then covered with a layer of clay and silt and then maybe limestone. You know, there's all kind. In your case, you have no stone there because you can get right through. But in any case, these things with under the when you have groundwater, and the groundwater fluctuates, so that will make these things mobile. They could actually get trapped. You know, there could be, for example, I could imagine that there might be variations in these kinds of structures in the ground where they kind of trap into deposits like this. Maybe the process is different from what I'm imagining here, but from what you're telling me. So what I would do is I would focus on finding traps like this. And then I would come in, once you have an area that's not disturbed, right? Then you would come in with your jet and try to hit that, okay?
Okay.
And then you're going to basically say that, oh, you know what? These structures are associated with this, or they're not. So then when you find these type of structures, there's no point in going and exploring those further because you've tried it and it doesn't work. So you see that you kind of have to...
Trial and error.
Well, it's ground truthing. So in geophysics what we do is that we drill holes usually, or we use other complementary techniques to kind of mitigate the risk of and the cost in finding whatever you're looking for. So because drilling a hole or putting the pump down there, you know, it takes time and effort and things like that, and you're trying to be more accurate, so you don't have to excavate the whole area, right? So that's the approach I would take.
So the example that you were showing here, that there's something happening below surface as groundwater or nothing, and then the clay silt, layer of clay silt. So you're saying it should get pushed up and get hit against that layer of clay.
Well, think, you know, this stuff wants to float, right? Compared to sand. Sand and, you know.
Right. So if there's a body of water under this, where does that put us?
The body of water under here?
Yeah.
Oh, like the ground table?
Right. We
the water
haven't.
table?
We have to. One thing is that there's no technology out there, and for us to even get out there, that's going to cost an arm and a leg to get surveyed for what's down there. If there's even if you want to put in a well, they do it blindly. So
Yeah, right, and that's the thing that we come up against. Some guy's a water witch, right?
right,
$50 and he'll tell you where to find water.
right,
Well, the truth is there's water almost everywhere. It's just how much do you want? Find quality water.
right. And so we know that they said we've been told that there's lots of water beneath the surface. We're not sure about the depth. They're trying in the process to figure that out. But what I was asking is that what relation would that have as far as if there's water below the surface, then we've got sand and then clay. Would that push it up, push it down? What do you think, in your opinion?
Oh, if you have water? Well, water is a very dynamic process. The things that cause erosion and what's caused, our earth is air and water.
Mm-hmm.
So water will move through the ground, even as it just sits there. This is called a groundwater or aquifer. We use it to drink. The reason why we're not running out most of the time is because the water keeps flowing back into our wells, right?
Mm-hmm.
That process over millions of years may cause us to be somewhat mobile. Maybe my assumption is totally wrong here. Maybe it's that you had this lithified, amber. Is it still? It may still be in its same state as when it's like deposited or left there. Maybe it's stuck to something down there. I don't know. I can't tell you about that. But I would say that this is how I would expect it to behave. There's probably a lot of research out there that you can find where people have actually studied this type of thing.
I've looked, it's pretty minimal.
Yeah, well, you may not have looked in the right place.
Okay.
There's in my field, it's geophysics, so it's like a physics major with a minor in geology, kind of like that, right? So we apply physical phenomena, we make measurements from that to imply some geology. So you need to be in like those type of environments, or industries like geology, geophysics, mining, maybe gemology. Like real research, not like what some guy just says happened in his backyard. Like papers, peer-reviewed papers. There's always, if there's an interest in amber and there's an industry people are looking for it, there's going to be scientists studying it. I'm certain of that.
Okay.
That's how I would do it. I think maybe you said you had 2 locations, one here in North America and one in Ukraine.
The Florida the terrain is similar where we can actually take a bunch of it, drop it down there and test it and see what it works out. We have a site in Jacksonville with a little bit over 5 acres.
Yeah.
And it has similar type of ground or the terrain in it that I think we'll be able to simulate the situation.
Well, for my purpose is that how do you get the amber down there? And
excavated.
Well, that's the problem. You will detect the excavation of it, so that will basically be what you see. And I think with a lot of geophysical techniques, that's the issue. And the other thing is that you don't know how it's naturally occurring down there. That's the problem, is we can't see it. And the only way to know is to dig it up. Then you've destroyed the evidence, kind of, in a way. So we have to apply...
I see what you're saying.
And this is common for many situations where they're looking for something we haven't done before, is that you're trying to understand how this occurs and naturally, because you want to use that information to see how can I perhaps look for those conditions, those geologic conditions that are preferential to finding these. I think that you just have to do some ground truthing. Do some measurements and see. Then come back with your normal type of exploration. You just go start pumping and see where you get stuff, and then you can look back at your image and you say, okay, I think it's really associated with these locations, more conductive areas, for example, and more resistive areas, or structure. That's another thing. Because the amber itself, you need quite a bit for it to really register as a more resistive unit, right? Because, if you take a cubic meter of this material, and then you have some amber, if you have one piece in there, or if you have 50% of it, it's going to have a big difference in the pathways for the current to flow, right? because this will inhibit it. I'm certain of that. So I can't tell you, somebody who's actually done this before, but that's kind of the issue, isn't it? Because it's a very precious resource, and so everybody's very quiet about where they have it, because you don't want to tell this guy to come and research it, and then he figures how to do it, and now he makes everybody else successful at doing it, right?
Right.
So, in any case.
So in reference to, I'm just going back because the idea was to rent the equipment, take it to Florida, and
Yeah.
run it and see what we're able to get out of that.
Yeah.
In reference to
Mhm.
when you say if we disturb the ground, we're not gonna see if we're gonna bury something down.
Well, you're going to see the disturbance in the ground. The same way as that when we're looking, when our clients are looking for old culverts or tanks or pipelines or utilities in the ground, we don't actually detect those typically directly. With a conductor or fiber optic in the ground, we're not going to see. It's too small, right? So what we see is the trench that they dug. That's really easy to find, because you took the material, removed it, and put it back. So you kind of took and mixed it up and put it back. It's no longer same as when it was deposited naturally.
What if we were to build a box or even dig a hole and deposit sand in there, and like in layers, and drop some of the amber in it and deposit some more, pour water on it,
Yeah.
and then try to read it? Would that create a similar situation to what was prior to
Absolutely.
disturbance?
Now you're doing exactly what geophysicists do. The way that we work is we start with tub models or sandbox models, and maybe acrylic on the sides, fill it with a very uniform sand, so that you take out the complexity of you try to simplify it by taking out the geology out of it.
Mm-hmm.
Because can I measure this? And what they do usually is that they use plastic blocks or PVC pipe to see if they can see resistive features that
Mhm.
kind of would simulate it. You wouldn't even need a lot of that, because
Right.
I would imagine that's probably a very expensive piece. So if you want to create different types of situations where you think it could be seen, then yeah, that's definitely how you do it. And you would just instead of having this long cable deployed, you would maybe just have nails, stainless steel nails, and then just hook up conductors. This is a 56 electrode box, so each pin here corresponds to a takeout. We have a wiring diagram, so you would know exactly how it would, you would just solder in to a connector. You buy the connector from us, and you solder in the conductors, connect them to, like a little rail with little nails on it.
I see.
You don't even need to do sand. I would just do like water, because that's much easier to work with. And it just comes out of the tap. And that's very uniform, right?
The idea behind the sand is that we want to create a similar environment as we would on the ground.
Right. But to make it even simpler for you, before you put a bunch of sand in there, you just fill the tub with water. Try it first with that.
That's a lot of water if we're going to go 30 meters or even 15.
Oh, no. You have to scale it down. So this scales at any size, right?
Okay.
So you maybe do it like, small box. It doesn't have to be very big at all.
Oh, I see.
Yeah, I'm talking about like a laboratory experiment where you don't have to mobilize to the field and spend a lot of money on doing that. Till you see, hey, can I detect it just with a simpler problem? Then make it more complex. Then, hey, you know what? Let's take this box now. Let's go ahead and fill it with sand. Let's do a measurement. Now let's fill it with halfway full of water. Do a measurement. Then fill the whole thing with water and sand. You see? Then you can deploy to making an even bigger experiment. This is basically how science goes, because you're always asking for money from some source. If it's National Science Foundation, they want, before they tell you, okay, we're going to give you $100,000 to go out and try it out here, and excavation costs, maybe it's even more than that. Try small model. Can we, does this look like this would work? And then try to scale it up, from that point. So your investment is less. I mean, the amber's not going anywhere if you own the property, right?
The timing is the biggest issue, is because dealing with places like Russia and Ukraine and the continuous political events that take place, the rules and laws continuously change.
Yeah.
So you can get a license for an area, start excavating, and 6 months later somebody will come in and take it from you.
Yeah.
So that's where we have an opportunity window now.
Okay.
If it flies, then we need to act on it, and because we don't know
So-
what's going to happen.
In that
6
case,
months.
my suggestion is this. You know, we have a saying here, and it's a Swedish saying. I'm Swedish originally, my family is, and one of the founding engineers here is also Swedish, and he says, "Att mäta är att veta." It rhymes in Swedish. It means to measure is to know. You can postulate on things until you just go and make the measurements. Take the equipment, go make some measurements. From that data that you have, then try to explore those different features you find and see where you're more successful. If you find that you find a repeating type pattern, then it really makes sense to continue the rest of the area and use this kind of technique. That way you're not wasting time excavating at all. Only the key areas where you need to be, or if you're using the jet type. I would imagine excavating is the best thing, right? That way you can wash it and separate it easier. But it's more costly.
Right. We have to look at if there's a vast amount of it in there, then yeah. If it's clusters, then it'll be more cost effective to put 2 guys on it in a pump and let them at it. It again depends on the area. If there's trees, what the rules are as far as what we can and cannot do. Obviously, we can't go in there and start destroying
Right.
habitats.
Right.
So there's lots of different applications.
So the way I can see this occurring is that, yeah, you could go out there and then you have this exposure because you have to mine a large area.
Mm-hmm.
People start wondering, what are you doing?
Right.
And then they find out, oh, it's amber. Suddenly you have people around you doing the same thing because, people see opportunity, right? So one way, I guess the obvious thing is it even worth it doing the surveys and spending the money on equipment, or is you just send a bunch of people out there and explore an area very quickly and get it done and then get amber and then you're kind of in and out? But then you have a lot of exposure, right? Or is the other thing that you do these surveys and people are, what are they doing? Because when you have these stakes there, nobody really understands what you're doing, right?
Right.
So then you get a lot of information without doing anything. It's like remote sensing. With that data, you can come in at a very, very quickly come in, try some certain areas, have less exposure to people seeing what you're doing, and see if you can correlate that. Take that information back to where you're at and think about, give yourself a strategy how you're going to go next. What are you going to do next? So in some cases, that if you're dealing with officials, you don't want you to destroy the habitat or the property, for example, or the groundwater. You could potentially hurt the groundwater that maybe some farmers using. Not exactly sure how to apply in your case.